let's take a look at resolution. So resolution in physics refers to the ability to distinguish two objects as being two distinct objects in an image. Another piece of vocabulary is, if the objects can be distinguished, we say that they are resolved. Now, we have a standard way to judge whether or not objects are resolved, and you can imagine that, if we didn't have a standard way, two people might disagree on whether or not the objects are resolved. But this standard way to judge whether they're resolved, called a criterion, is called the Rayleigh Criterion. And the Rayleigh Criterion states that two objects are considered resolved if the central max of one is at the location of or further away than the first minimum of the other. And I'll draw a diagram to explain what I mean. So imagine that we have light passing through a slit, an aperture. So like in a camera, say. Passes through the aperture, and there's two objects that are sending light through that aperture. So we're going to get two different single slit patterns over here. So let's say we have a red object and a green object. The red object is going to create a pattern like this. The green object is going to create a pattern like this. The Rayleigh Criterion states that they're resolved if the central max of one is at the location or further away than the first minimum of the other. In this case, this green pattern is further away than the first minimum of the red pattern, so they're resolved. I'm going to draw a different one. Let's say I have these two objects. They have patterns on a screen, so here's a red one and a green one. In this case, the central max of the green one is exactly at the at the first minimum of the red one. So here they're just barely resolved. That's at the limit of resolution. And then let's draw a third situation. So in this case, the central maximum of the green one is within the first minimum of the red one. So here they are not resolved. They're too close together and they would appear as a single object rather than two distinct ones. Now, the angular distance between the central maximum and the first minimum for a single slit diffraction pattern is given by theta is equal to lambda over b, where b is the slit width. Or sometimes it's written as theta is equal to lambda over a, where a is the slit width. Either way, theta is equal to lambda over the slit width. Turns out that if we have a circular aperture, like for a telescope or for the human eye or for a camera shutter, the angular distance from the central maximum to the first minimum is given by theta equals 1.22 lambda over b, where b is the aperture diameter. So there's this extra 1.22 when we talk about a circular aperture. Why? Well, the simple answer is because it's a circle and circles behave differently than slits. If that's not satisfying, the more complicated answer is that it comes from something called a Bessel function, which you usually don't encounter until part of your way through college physics. And I can write down the Bessel function, and you can see why we're not going to worry about it this time. So either way, you don't have to understand why there's a 1.22 in there, but you do need to know that that 1.22 is there because we're talking about a circular aperture, not just a slit. Now let's shift gears and look at resolvance in a diffraction grating. So we've seen before that if we increase the number of slit maxima in the pattern on a screen, so for instance, if we have a 2-slit pattern, this is what it looks like. If we increase to 10 slits, light passing through 10 slits, we get larger dark regions and narrower, sharper, bright spots. And if we have 1,000 slits that light passes through, we get very narrow, very sharp, bright spots. However, even if you send light through many, many slits, there's a width to these maxima. They're not infinitesimally sharp or infinitely sharp. That means that if we're trying to resolve two different wavelengths in a pattern on the screen, then if they're too close together, we might not be able to resolve them. And I'll show you what I mean. I'll try to draw this. So let's say we have fewer slits that are illuminated, and we have this kind of pattern. We have green light and red light passing through the slits, and we get something like this. So green light has a smaller wavelength, so the green maxima would be closer in. than the red. That central maximum, that's for n equals 0, and then we have the n equals 1, and the n equals 2, and the n equals 3 peaks. And these are called the first order maxima, second order maxima, third order maxima. That's the language that we use. So in this situation, notice, for the first order maxima, for the maxima that correspond to n equals 1, we do not resolve the green and red light. The green and red light is mixed together. The peaks overlap. But second order maxima, the third order maxima, they are resolved. Now, let's think about what would happen if you send light through even more slits, so many more slits. Then the peaks will be narrower, and we would get something that looks maybe like this. So because the peaks are narrower, because these first, second, and third order maxima are all narrower, now we are able to resolve the first order maxima from the two different wavelengths. So this all can be summarized with something called resolvance. We define resolvance for a diffraction grating as this capital R, has no units, and it's equal to lambda divided by delta lambda, where lambda is the wavelength that we're considering up here on top, and delta lambda is the smallest wavelength difference which can be detected by this diffraction grating. And this is equal to capital N times M, where capital N is the number of slits that the light passes through. Sometimes they say the number of slits which are illuminated, because that's how many slits the light passes through. And then M is the order of the diffraction pattern. So it's either M equals 1, M equals 2, M equals 3, so on. If we have a large value of R, a large value of the resolvance, that indicates that this delta lambda is relatively small, and so smaller wavelength differences can be detected, and it has better resolution. So a large value of R means better resolution of wavelengths. And resolvance will improve when light passes through more slits, because capital N is greater. And the resolvance also improves, notice, at higher orders when you have larger values of M.